Hello, Precalculus students, and welcome to our notes for the week of April 6th. This is Mr. Gallagher here with you today, and we will be looking at section 2.5, which is our rational functions. So hope everybody's doing well. Before you get started, if you would like to print out some of the things from the module for this week, I think that would help you out a lot. The two things you might want to look at are we have the notes for rational functions, which is a printout of some of the topics we're going to be going over. And then there's a worksheet as well on rational functions for section 2.5. And that's 7 problems, and I'm going to be doing 2 of those problems with you to kind of get you started for what you need to do for this week. So if you want to go ahead and hit pause and print those out if you haven't already, or if you just want to follow along with the video, that'd be great, but we'll wait here a second, and if you want to go ahead and hit pause, and we'll be back in just a moment. Okay, here we go. Hope everybody's ready. So today we're talking about rational functions, and what rational functions are when we have a polynomial on top of another polynomial. So if you looked at, remember last week we looked at polynomial functions, and none of those, as it says here in the notes, none of them had denominators, right? They were all just expressions and terms and constants and variables, but they were all without a denominator. So now what we're going to look at today, we're going to look at where I have a polynomial on top of another polynomial, and we're going to call this P of x and Q of x. And there's different types of rational functions. In fact, these are the 3 that are listed. Bottom heavy functions, where the degree, remember the degree is the largest exponent. If the degree of the bottom, the Q of x is larger or higher than the degree of the numerator, P of x, we call that a bottom heavy function. Top heavy is just the opposite. Top heavy functions are where the degree of the numerator is higher than the degree of the denominator. And then powers equal functions are where the 2 degrees are the same. For this purpose, we are not going to be discussing top heavy here. We're just going to be talking about the bottom heavy functions and the powers equal functions. And that's what we're going to cover in this lesson. So before we look at some examples, I want to go over briefly some different terms and characteristics of these functions that we're going to be going over as we graph them, because we're going to be looking at graphing these rational functions today. So we're going to be talking about the domain. What's the domain? The domain is all the possible values of x, and whenever we look to find it, the best way to find a domain is to always find out what x cannot be, right? And then the domain is going to be everything else. So what can x not be? Well, x can't be a square root of a negative number, right? And we also can never divide by 0. So for our domain, we're going to set the denominator equal to 0, and that's going to tell us what x cannot be, right? Because wherever x is going to make our denominator 0, we know that cannot be a valid value of x. So that's going to help define our domain. We're then going to look at asymptotes. We're going to look at our vertical asymptotes and our horizontal asymptotes. So remember the vertical asymptotes, asymptotes we've seen before, right? We've seen asymptotes when we were graphing hyperbolas. We saw asymptotes when we were graphing a tangent and cotangent graphs, right? These are lines that help shape the graphs, and these are lines that primarily tell us what x cannot be in most cases, and it also helps, again, it's like shape the graph and shape some of the end behaviors as well. So the vertical asymptotes are vertical lines, and these are lines in the graph that x cannot be. In the tangent and cotangent graphs, we saw this where the tangent was undefined. Same thing here. We're going to see our vertical asymptotes when we set our denominator equal to 0. These are going to be values where the denominator cannot be 0. For our horizontal asymptotes, these are going to be horizontal lines. And these will all become a lot clearer when I do the examples. But for our horizontal lines, there's going to be 2 different situations based on whether or not it's a top heavy, bottom heavy, or powers equal. Again, we're just going to look at bottom heavy and powers equal today. If it is a bottom heavy function, then my horizontal asymptote is always going to be at y equals 0. So a horizontal line right on top of the x-axis. If it's a powers equal rational function, then the horizontal asymptote is going to be the coefficient of the numerator's highest power over the coefficient of the denominator's highest power. And we looked at those before when we were looking at odd and even functions, and we were looking at the leading coefficient. That's what we're going to be looking at here as well. Finally, the last few things is we're going to be looking at the zeros, the roots. What happens when y is equal to 0? Where does it cross the x-axis? How do we figure that out? Well, we're going to set y equal to 0, which means the numerator is going to be equal to 0, right? So it's the top number of our fraction. If that is equal to 0, that's going to be where our zeros occur. And then we're going to be looking at, I'm going to skip interval work for a second, but we're going to be looking at the y-intercept as well. Where does it cross the y-axis? And we're going to do that by setting x equal to 0. And all these are going to help us find our graph. And then finally, we're going to do what's called interval work. And we're going to do it a little bit differently than it says here on this chart. It talks about coming up with a sign chart. We're actually going to just plug in different values to help us graph our rational functions. So that's where we are. And I'm going to explain these terms a little bit more as we go through, but let's do some examples. And this is on the worksheet. I'm going to do examples number 1 and 3 from the worksheet to help you graph these rational functions and give you some guidance, and then you can complete the rest of the worksheet yourself. So the first thing we're going to look at is this function right here. Y is equal to x minus 4 over x plus 2. So what do we do? Well, the first thing we do is we're going to go through that order. We're going to find the domain. So how do we find the domain? If you go back up here on our chart, it says we're going to set the denominator equal to 0. So the denominator, the bottom, I'm going to set that equal to 0. So where x plus 2 is equal to 0, we know x equals negative 2. So what does that mean? Well, that means that the denominator, if I set it equal to 0, x is going to be negative 2. That means x cannot be negative 2, right? Because that's where we would divide by 0, and x can never have a divide by 0. So what's my domain going to be? It's going to be everything except negative 2. So how would I write that here? Well, in interval notation, I would say, well, my domain is from negative infinity to negative 2, and then from negative 2 to infinity. And that's going to be my domain. And get a smaller pencil here. That's going to be my domain. And there's the next spot that talks about holes, and I'll actually do that in the next example. This is not going to be applicable to this particular example that we're working on. So now let's talk about, it says VA and HA. That's my vertical asymptote and my horizontal asymptote. So again, the vertical asymptote is where we're going to set the denominator equal to 0. Well, we already did that, right? We already said my domain, when I tried to figure out my domain, x cannot be negative 2. Well, then that means my vertical asymptote is going to be at x equals negative 2, because that's a value that x cannot be. Horizontal asymptote, as it says up here, the horizontal asymptote depends on whether or not this is a bottom heavy or a powers equal function. Well, if you look at the original rational function we have, it's x minus 4 over x plus 2. That is a powers equal, right? Because x to the first over x to the first. So for this case, my horizontal asymptote is going to be the leading coefficients of my two highest exponent terms. In this case, it's going to be 1 over 1, because there's a 1 in front of this x and there's a 1 in front of that x, right? That's implied. So my horizontal asymptote is 1. So it's going to be y is equal to 1. That's what I have so far. So let's graph this. Let's graph our asymptotes. So my horizontal asymptote at x equals negative 2 over here is going to be a horizontal asymptote right there at negative 2. And then I've got a vertical asymptote at, I'm sorry, that was my vertical asymptote at x equals negative 2. My vertical asymptote, my horizontal asymptote is at y equals 1. So here is my horizontal asymptote at y equals 1. So my vertical, x equals negative 2, my horizontal asymptote at y equals 1. Okay, next thing we need to figure out is my zeros and my y-intercepts. So how do I do my zeros again? Up here it says, to find my zeros, I'm going to set my numerator equal to 0, right? Because the fraction will equal 0 where the numerator equals 0, 0 over something. So what is my numerator? So for my zeros, I'm going to say x minus 4 equals to 0. That means x is equal to 4. So that means my 0 is going to be at the coordinate 4, 0. And what about my y-intercept? My y-intercept, as it says here, is we're going to set x equal to 0. So wherever x is equal to 0, that's going to be my y-intercept. So let's plug in for my y-intercept. I'm going to say 0 minus 4 over 0 plus 2. And that gives me negative 2, right? Negative 4 over positive 2, which is negative 2. So that means my y-intercept is going to be at 0, negative 2. So I can plot those 2 points as well. I've got 4, 0, which is going to be right there on my graph. I've got 0, negative 2, which is right there on my graph. And now let's talk about the interval work. Interval work is where I would plug in some numbers that would help shape my graph. Well, if you'll notice, I've got 2 numbers already. I've got 2 coordinates that are already to the right of where x equals negative 2. That's this part of the graph right here, this right-hand side, but I don't have anything on the left-hand side of my graph when x is less than negative 2. So I'm going to try a couple of values. I'm going to plug in some numbers for x that are less than negative 2 to help give me an idea of what this graph looks like. So I'm going to say, what happens when x equals negative 3? Well, when x equals negative 3, I'm going to get negative 3 minus 4 over negative 3 plus 2. And that's going to equal 7, right? So one of my points is going to be negative 3, 7. And let's plug in another point. So negative 3, 7. So negative 3, 7 is going to be a little bit off my graph. It's going to be way up here. And then let's try negative 5. So if I plug in negative 5, what's going to happen? Well, when x equals negative 5, I'm going to get negative 5 minus 4 over negative 5 plus 2. And that's going to be, what, 3, right? So negative 5 comma 3. Negative 5, 3 is about right there. So those are the points. So now what is this graph going to look like? Well, the asymptotes are going to help shape my graph. So I can go ahead and sketch my graph. We'll do it in another color here. And my graph is going to look something like this. I'm going to have a curve right through these points. It's going to get really close to my asymptotes. And I'm going to have a curve right here that again is going to get really close to my asymptotes. So this is the graph of that rational function. It's 2 curves that are shaped by the asymptotes that go through the points that I looked at. The last thing I want to look at here is E and F. I want to look at my asymptotic behavior. I want to look at, and the end behavior. I want to look at some limits. So let's do the limits that we already talked about first. Let's look at my end behavior. The end behavior is, what is my limit going to be as x approaches negative infinity of f of x? And what is my limit going to be as x approaches infinity of f of x? Well, what are those two going to be based on this on this graph here? Well, on the other ones we looked at, our answers are always positive or negative infinity. But let's look at this graph a little bit closer. As this graph goes to negative infinity, which is right here, this part of the graph, what does x get close? What does the y value get closer and closer to? It gets closer and closer to 1. So that's going to be my limit as x approaches negative infinity. What's going to happen over here as x gets larger and larger, closer and closer to infinity? My graph's going to get closer and closer to 1 from the bottom, right? So my limit is also going to be 1. So that is my end behavior. The last thing we're going to look at is the other asymptotes, the other asymptotic behavior, where it gets closer and closer to this asymptote right here, this asymptote at negative 2. What happens? Well, as x, the limit, as x approaches negative 2, and I'm going to put a little minus up here. And this little minus means the limit as x approaches negative 2 from the left. That means from the numbers that are less than 2. So I'm going to put a little minus up there. What happens as x approaches negative 2 from the left? Well, this graph is going to go up and it's going to get closer and closer to what? It's going to get closer and closer to that negative. Well, x is as x gets closer and closer to that negative 2, my graph goes up higher and higher and higher, and it approaches infinity. So I'm going to say that this graph, the limit as x approaches negative 2 from the left is equal to infinity. Likewise, down here, what happens? What's the limit as x approaches to negative 2 from the right, or from the numbers that are greater than 2? What's the limit of f of x there? Well, the limit of f of x is going to be equal to negative infinity, because you'll notice that this graph goes down further and further, all the way down past the graph, and continues on closer and closer to infinity. And there's my answers. So for the asymptotic behavior, I'm going to put on graph, because I listed those on the graph there. And there's our rational function. So I'm going to go ahead and clean this up, erase some of the little highlights here. And there's my graph. And I've noted the limits. I've got my asymptotes, and I've got the basic shape of the graph based on the points, the zeros, some of the interval work that I did, and I listed all the limits on the asymptotes.